Okay, guys, we'll kick off. So, welcome to the Predict conference series. This is webinar 3. I'm delighted to be out in the SAP App House here in Dublin. I'm joined by Dr. Paul Pallett, who has given us a tour of this very impressive setup here in the SAP App House. So thank you to SAP for hosting us today. We have a number of people on the line, so we'll kick off with the webinar. Very exciting lineup today, so thank you again to SAP for hosting us here in the App House. As I mentioned in previous webinars, the Predict conference is set up to be a little bit different to your standard conference in that we've combined 4 series into one major event. And this webinar is our 3rd webinar as part of the knowledge series. So what we're trying to do is to build up knowledge on the parts of attendees, get to know the speakers, think of some really hard questions that you can ask them on the day of the big event. So this is your chance now to take some notes, so to come up with some really tough questions. You can submit your questions today, by the way, for both speakers using the chat box on your WebEx system. And as I said, please feel free to ask those questions and think of some really hard ones. That'd be great. So this is the knowledge series, which is part of the webinars leading up to the conference, which happens in September, clearly. And we have revision webinars following the conference. We're going to create an ebook and articles coming out of the event. The conference also is obviously really all about the speakers. So we have great speakers coming from all over the world, where you can meet those speakers at the event in September. You can meet them online during the webinars, and there'll be great case studies showcased, including the ones today. Don't forget about the Connector series as part of the conference. So once you register for the conference, you can request meetings and put your profile forward through our partner EEN. So once you register for the conference, you'll get an email explaining all the details, and we'd encourage you to make the most of the Connector series so that you can meet the people you want to meet at the conference. And finally, and the most exciting part for us data scientists, is the data series. So at the event, we'll have a range of data science experts, and they'll be identified by their Data Genie t-shirts, and they will be making introductions at the event. So if you're interested in text analytics or sentiment analysis, they will know the people at the event who you need to talk to. If you're interested in risk analysis or quantitative analytics, they'll also know the experts at the event that you need to talk to, and they'll be able to answer questions. So this will be really exciting, and they'll be introducing you to live data innovation on the exhibition floor. And finally, we'll be demonstrating our expert models platform at the event, and you will be able to access that and after the conference. So we're really looking forward to the 4 strands of this conference series really coming together. I'd like to thank our partners who've come on board for this event. We have SAP who are hosting this webinar, but also we have some major partners who are contributing a lot to this event, and they're going to be present in order for you to meet and talk to these people at the event. So thanks to Aon, who've come on board since our last time I spoke to you, and also of course to Mazars, the Boston College Global Leader Institute, Bank of Ireland, Sigmar, and all of these other partners who I've mentioned before, who are really contributing a lot to the event, and without them this event couldn't happen. So again, great to have all these partners on board. If you're interested in getting involved, we're still open to discussions on partnerships, so please do contact myself or Amit, and we would be delighted to talk to you about that. So without further ado, I would like to get started on the main event for today. And our first speaker is Dr. Paul Pallett, who is the Chief Data Scientist and Director for Advanced Analytics at SAP, based here in the App House in SAP Dublin. So it's great to have Paul here in Ireland working on this advanced area. So I'll shift over all the way in a second. But Paul has a background in electronics, telecommunications and computer applications, and a PhD in machine learning. And today Paul will be speaking about SAP's views on the future of analytics with specific focus on the enterprise. So again, please do submit any questions you may have, and over to you, Paul. Thank you very much.
Thank you. Thank you for that wonderful introduction. I will switch into my slides here. So thank you for this opportunity given for SAP to share their views about the landscape of advanced analytics in the enterprise space here. And this is how I think I will talk about what I want to do. I'll talk about the analyst view of advanced analytics and the major innovations in that area, the future of analytics infrastructure, some key highlights of the survey that we had, and SAP offerings.
Could people mute their phones, please? We're hearing a bit of noise on the line. Thank you.
Okay, what I did for you, I'm just going to finish off something. Okay?
Yep, so going ahead with the discussion here, if you look at the Gartner hype cycle and in 2009, and if you look at the entire curve here and all the key points that are highlighted here, there is very little about big data, technologies, IoT, and so on, right? Nothing much which comes out of the hype cycle here. But then 2 years later, if you look at the hype cycle of emerging technologies in 2011, you find mention of the initial technology triggers in big data. You have natural language processing, IoT, speech translation, and so on. And predictive analytics, if you find, it's in the scope of enlightenment. That means that there are success stories that people had to share in terms of their successful implementation of predictive analytics technologies into their business applications, which is further strengthened in the next hype cycle, telling that okay, predictive analytics is now mainstream. If you look at the last two hype cycle that has been released by Gartner, and if you look at the colored bullet points here, you can find that there is a significant pace at which the technologies have shifted from the trigger of innovation towards the scope of enlightenment. Currently, most of them have some initial implementations that are there. People are looking for success stories. There are a lot of failures also which are reported. But then these technologies are moving faster and faster with all the unknowns getting unsurfaced over the entire life cycle. Things are becoming better. But this also tells us that with all the different technologies that are coming out, there's a lot of digital footprint that each person leaves, whether it's a person or a machine. But the interactions that the person or a machine has with the digital ecosystem leaves around a lot of information that can be mined, or machine learning algorithms can be applied on top of that to make things more smarter. And now if you translate that into the entire analytics infrastructure space, you have BI. So BI is more about understanding what has happened with the data after an event has occurred, right? So you have descriptive analytics and diagnostic kind of use cases that are available as part of the business intelligence workflow. This is one extreme of it, wherein the insights are, or the visualizations, the storytelling is done by humans so that another human can understand and make sense. But this is all about post-analysis. On the other extreme, you have advanced analytics, wherein we are trying to understand what is going to happen next. And this is specifically completely maths, which is powered for consumption using processes. And definitely there is a lot of overlap between BI and advanced analytics. And even in the field, when you talk about advanced analytics, people are more talking about BI than advanced analytics, right? And that fuzzy area is more about the exploratory analytics, wherein you have maths, which are the entire analytics powered by maths, but it is being represented for easy consumption by humans. And this is one area wherein I think in the Predict conference in September, we'll have a focused discussion around exploratory analytics by Eric Mcnamee. So if you translate this particular slide into even more a different perspective of it, you find that as you move from the left to the right, the type of research that has gone in, the complexity of the algorithms that are there are going to be even more complex. But the quality of the insight that comes in towards, as you move from the left to the right, are more actionable, and it engages the user more as you go across from the left to the right. So you start with what has happened. It's more traditional reporting to what can happen best. And this entire workflow from end to end actually gives you a possibility of telling an end-to-end story of what has happened and what is going to happen next from embedding predictive workflows in your business applications. Now, looking at people who would be part of that entire journey, you have data scientists, right, who are traditionally a small percentage of the people who understand advanced analytics to the core. They know the algorithms, they are able to actually churn information and come out with intelligent insights that are actionable. But if the industries are building just tools for data scientists, you are addressing a small population, and that is where the entire focus of the industry is shifting to. Because people, the decision makers are the business users. They need actionable insights so that they can take decisions understanding what is going to happen next and generate a lot of revenue on top of that. So any data science product should be focused on the business user more than the data scientist, but it should also have a capability of easy consumption of data scientist models into the business user workflows. And that is exactly why advanced analytics is also at a stage wherein traditionally you had models that were built on transactional systems, right? You understand the customer from either the transactions that he has done on the ERP system or on the CRM system or your traditional transactional systems there. And when you build models using that, you are only limited by whatever information is available on those transactional systems. But then today, with all the technological advancements that we have seen till now, enables you to augment the information about the user with all the other digital interactions that the user has had on social media, on email interactions, on the way he actually moved around the world, the click streams, the interactions on the mobile devices and so on, which actually enables you to understand more about the consumer and making it difficult for you, because this challenges, this leads you to another challenge, which is the big data challenges. And we are all aware of the various complexities that big data brings forth when you look at it. But then there is another complexity here. The decision cycles have become faster. Traditionally, earlier, you had 3 weeks for a PC to be built once you order. But today, people want it on the same day or maybe in the next day. And if you look at traditional algorithmic trading, 30 milliseconds was good enough maybe some years back. But now it's more, because of a lot of people doing it, 5 milliseconds, and even people are going to microsecond kind of an information. And when you look at all the machine learning algorithms, these are highly iterative. You have to churn huge amount of data to make a decision at that spur of the moment, and that is even more challenging. And on top of that, the people who understand analytics, or people who can build robust models, are rare. There are very highly few skilled people, and that is what McKinsey actually states, that the supply and the demand gap is going to be more than 50 to 60%. And what this enables, or this leads us to understanding that it needs automation, significant automation. Most of the workflows that a data scientist can actually do should be automated for easier consumption and for faster turnarounds. Why should I care? Why should we talk about advanced analytics? And these are a few highlights from an SAP survey on the advanced analytics consumer behaviors for some of the implementations that have been done across the ecosystem. And 90% of them agree that predictive analytics, or embedding predictive into their business workflows, have given them significant competitive advantage. People also say that the data that they were working on a year earlier has now almost doubled, right? So the challenges are increasing. A lot of data, a lot of diverse amount of type of data, the quality of data, but then it is not a deterrent, because there is a lot of value when advanced analytics is embedded into business applications. Now this is a typical problem, right? When I started my career, I had some information which was available to me by which I can build models. But then to make the models robust, right, and even performant in terms of the accuracy at which we are able to predict things, I always used to think, I need more information. But now, with so much of information already available, it's always a question where to start from. And that is where possibly SAP helps big time. This gives a small flavor of the SAP portfolio. I don't want to spend much time here, but it tells you that SAP has the entire portfolio, which starts from people with absolutely no skills about advanced analytics, and to the entire persona of people who, with advanced skills. So you have offerings which goes from business user to data scientist, but any complex scenarios that are created by the data scientist are made available to the business user in terms of easy consumption scenarios. And there is a lot of automation all through the entire value chain. This is how the entire advanced analytics portfolio for SAP looks like. You have SAP HANA as the center of the entire portfolio. There are a lot of highly, optimized algorithms on HANA which is provided. You have connectivity to multiple different data sources. You have industry-specific applications as well as partners who can actually build on top of these capabilities. We have a client tool that helps the data scientists to build complex models. That is the predictive analytics offering that we have. And we have specific tailor-made algorithms which are part of the predictive analytics library as well as the automated libraries which are available. And we are open to R. So you have a lot of R algorithms that can be brought into the mix and run on HANA. This is the last slide. It just gives you a flavor of things that you can expect when you actually open up an advanced analytics product from SAP. You have a lot of automated algorithms that eases out your initial model building process. The obvious questions are addressed by the automated approach, but if you have complex scenarios, there is a workbench that actually helps you drag and drop algorithms, stitch together a complex chain and run it on HANA in database. I think I'll stop there and hand it over to Ronan.
Thank you very much, Paul. Really interesting overview of SAP's area in data analytics. So I think when we see such a large-scale organization of analytics, it's true to say that the time of data is truly upon us, and it's a major challenge for industry. So I'm going to come back to questions at the end. So now I'd like to introduce our next speaker, who is Dr. Brian Mcnamee, who's a professor or lecturer in the School of Computing at UCD. And at the Predict conference this year, Brian is going to give us his take on, he's going to give a masterclass on deep learning, which I'm really looking forward to. So this is a great opportunity to get a preview of Brian's talk. To give you a small bit of background, as I said, he's a lecturer in the School of Computer Science in UCD, and he's a principal investigator at CDAR, the Centre for Applied Data Analytics Research, which is a great initiative here in Ireland that the universities are collaborating with industry in order to solve technical problems around data analytics. He has a lot of experience in the area of analytics and teaches this stuff every day. He's written over 70 publications, and recently he's written a book called The Fundamentals of Machine Learning for Predictive Data Analytics, Algorithms, Worked Examples and Case Studies, and that was published just this year by MIT Press. So I'm going to hand over to Brian now, who's going to present from his office in UCD. And again, please feel free to submit questions by chat, and we'll pick them up here at SAP. We will ask the speakers at the end. And I've got some good hard ones for them as well, so don't worry if you can't think of one. Thanks very much, folks. And over to you, Brian. Brian, please share your screen now.
So I'm just looking for the share screen.
We're just waiting for the screen here to be shared. Can you see it now, Brian? We can hear you anyway, which is good. Okay, we see your slides. Now we can't hear you, Brian.
Oh.
Okay, we hear you now, yeah.
I can. So, thanks very much for that introduction. Hopefully you can hear me now. If you can wave if you can hear me okay. That's great. So I suppose like everybody else, the Predict conference when it comes around, I'm going to talk about deep learning. Very short learning here, just to give a flavour of the kind of things that we're going to talk about. I suppose that one of the reasons why I decided this would be a good topic to talk about and Predict is stuff in the kind of general media at the moment about artificial intelligence and machine learning and the dangers of machine learning. So this is a sampling of some of the headlines that have been around. And a lot of this is a bit hyperbolic, a bit over the top, but there are some interesting new developments, and in particular, a lot of the kind of the impetus for these articles comes from the development. An interesting thing to do to look at kind of the rise of new techniques is always to look at Google Trends. I'm sure lots of people have used this, but this is kind of fun to look at. If you do a search on Google Trends for the phrase deep learning, you can see it didn't really exist before about 2007, then it rumbled along for a little while, and then it exploded. So what we're going to do is look at what deep learning is, what it's not, and I'm going to do that by using a simple example. So this is a little sample from a big data set known as the MNIST.
We've lost your...
Here is learn to recognize...
We're losing your sound, Brian. And can others mute their line, please? And maybe use the phone again, Brian. Be great. This is fascinating stuff, but we can't hear you.
Okay. Sorry about that, so I'll try the handset again. Hopefully that'll work.
That's perfect.
Excellent. So this is the MNIST, or a little sample from the MNIST data set, and the challenge here is to build systems and train systems that automatically recognize handwritten digits. The MNIST data set has a massive collection of examples of the digits from 0 up to 9, and like I said, it's just a little sample of them. So what we want to do is build automated systems that learn to make those sort of predictions. And the standard approach to this is, before we try and train a system, we first engineer a high-level representation of that. So here we just have some kind of blown-up versions of a small sample of these images. And I want to show you what I mean by the kind of things we might include in a high-level representation. And here's where, in a machine learning task, domain expertise is really important. So we're going to bring a lot of domain expertise. We're going to talk to people about, what's important about recognizing handwritten digits. And we might come up with a simple feature, and that's the one I've got here, would be percent filled. So these are white numbers on a black background. We might measure the percent filled, and you can see, just with this little sample, there's some differences. So if you write a 7 or a 1, there's not many white squares compared to black squares. If you write an 8, there's a lot more. We might also then do some very simple image processing on this and get a skeleton of the images, and that would allow us to do things like count loops. So we can see there on the 8, we're going to take loops on that. The 7 has no loops. 2, this example has 1 loop. We can imagine lots of people would write a 2 that doesn't have any loops at all. So this is why we need lots of these features of representation. So we might add a few more, and here's a simple thing that people do for this kind of job would be, again, to look at those skeletonized orange lines across the letters and get a general sense of the direction that those lines are going in. So on the right-hand side of the slide, you can see there just a little compass, and there's 4 kind of key directions, so vertical, horizontal, or the 2 diagonals, and we might count up the amount of the white lines and the white pixels in these images that are going in each one of them. And the key thing that gives us is we've moved away from the raw images themselves to this high-level representation made up of these 6 features. So we represent each one of these handwritten digits as particular values for these 6 features that we've got here. And if we took a big data set, so the MNIST data set has thousands and thousands of examples, if we took a big data set like that, these features can all be automatically extracted from those pictures. We could train up a machine learning model. We might use a decision tree, would be a simple approach we take to this. We might use a decision tree to capture basically the patterns within each one of those images. And we could train up a decision tree using that high-level representation. And there's kind of an upper limit on how good you can make that system, and it's probably in the range of being able to recognize about 8 out of every 10 digits. Right, so if you imagine writing out a long number, throw this system that we train up at it, and it would probably get about 8 out of 10 right. That's reasonably good. That's 80% accuracy. But these kind of systems are used for things like automatic check scanning in banks, and obviously 8 digits out of 10 isn't brilliant for automatic check scanning. That's not going to cut it in the banks. And although engineering representation is one of the most important and time-consuming jobs in predictive analytics projects, and it's an interesting one that needs a lot of technical expertise and domain expertise sort of blended together, there is another approach, and that's where deep learning comes in. So deep learning is an example of a thing called representation learning. And the idea behind representation learning is that we start with the very, very raw data, and instead of using domain expertise to try and go to that higher level representation, we use machine learning approaches that can automatically extract those high-level representations themselves. This isn't new, right? So we said deep learning exploded kind of in the last few years. This idea of representation learning isn't new, and stretches right back. The earliest example that I'm aware of, at least, is in around the 1950s, and Rosenblatt and perceptrons, and the first kind of blush of neural network research. And I just want to give you a small example of how this kind of thing might work. So if we zoom right in on our number 8 here, we can see that the number 8, basically we have pixels. Right, so these images are 26 by 26 pixels. We can look at, 28 by 28 pixels. We can look at that grid here, and each one of those pixels has a number between 0 and 255, where 0 is black, 255 is white. And what I can do is I can split out the rows of that image. So I've just broken out the rows a little bit, and then attach those rows all in order. So on the next slide, if it's going to change for me, yes, there we can see the rows in order. So now what I've got is my 28 by 28 pixels, which gives me 784 numbers between 0 and 255, where each number represents the color within a pixel. And the 8 looks something like that. We can see a couple of others. The 5 looks like that strip. The 0 looks like that strip. So we can draw them, but really we just represent those as numbers. Now, we don't stress that you can't really see 8s or 5s or 0s in those, but we can see from this image that those strips are different. Yeah. And that's the key thing. And the key difference here is that we haven't gone to that high-level engineered representation. We stay down here at the very raw data. If we use a representation like that on, this is a simple multi-layer perceptron, which is a kind of a neural network. That neural network can be trained to represent or to recognize those different digits. We don't need to stress too much about what's going on in this diagram, other than in the very left-hand side, I think it's the left-hand side, I'm going to wave the arrow around, this has been mirrored, we can see that strip of pixel values. On the right-hand side, we can imagine these almost as little numbered light bulbs that are going to light up depending on what number comes in. And if we were to present the 8, and this is our strip of values from the 8, to this network, the 8 lights would essentially light up and tell us that that's recognized as an 8. So this is a predictive model, just like something like a decision tree would be. The interesting thing here is we've got this internal layer of what we call hidden units in neural network talk. But what's interesting about those, we don't have to stress too much about the neural network interpretation. What's interesting is these are learned high-level features. So that job I did of trying to recognize, we'll count loops and we'll count directions of lines, each one of these little circles represents an automatically detected high-level feature of that sort of character. We can see in the one on the top here, these pictures are sort of representations of what's being recognized at these. And we can see this top one is essentially looking for 2 loops. So there's just about 2 circles here. This middle one, we're looking for diagonal lines. And this bottom one, we're really looking for...
Brian, can I ask you something? If you go to your WebEx, I think you can mute the other lines. Just go participant mute all. Can you try that, please?
I'll try, yeah.
Great.
Alright, just looking for that option. Sorry, I'm just looking for where that is.
It should be on the top, near the file and edit button. Just go beside the edit button. There's a participant there.
Yes. Yeah, I got a participant, but mute all is grayed out.
Not there? Same for us. Yeah. Okay, sorry about that. Right. Please go ahead.
No,
yeah.
I'm almost done here anyway.
Yeah, no problem.
Thanks
for bearing with us.
No problem. So like I say, the key thing with this is that in this network has essentially learned high-level representations. We haven't put them in. We started with the raw data, and the system has done that itself. And a network like this will manage about 9 out of every 10 digits, probably a little more, maybe about 9.5. And this will do quite well. And this was kind of the state of the art for this kind of task until maybe 5-6 6 years ago or something like that, when these ideas of deep learning really started to bubble up. And the idea with deep learning methods they are representation learning methods. So it's the same idea as we saw in the last slide in the last example, but instead of having kind of single levels of that learned representation, there's lots and lots of levels of that learned representation. So this is quite a simplified example of what a deep learning network might look like for this digit recognition task.
Okay.
And you can see in the diagram I've drawn it purposely to look quite like the neural network we had before. The key thing is there's loads of layers here. Right? So there's lots and lots of layers, and that's where the idea, or at least part of the inspiration for the name deep learning comes from, that we have these deep layers within the networks. And the advantage in that is this idea of learning representations or automatically extracting representations from the data, we can do that at very low levels, and that's what the two little squares at the bottom of the image are to show, and ultimately at very high levels. So you can see the picture at the top, essentially that's an 8. And the idea there is that the network has encoded the characteristic of 8ness, essentially. So it's learned to look for that thing with 2 loops. And it'll do a really good job of recognizing 8s. This is kind of the high end for these sort of tasks, and deep learning approaches to this digit recognition problem will do just about perfect digit recognition within limits. If you do something really bananas with the way that you write your digits, it won't work, but just about perfect recognition.
Okay, that's good.
And that's where the rise of deep learning has come from. And one way to think about, why has this happened? An interesting thing in machine learning and building predictive models is this idea, the selectivity invariance dilemma. And the thing here is we want to look for patterns that are selective in terms of things that aren't important, but invariant to things that are really important. Right? That's what we look for. Essentially, we want to filter out the noise within images. Within data that we're looking at. Reason I suppose fall into images is these deep learning approaches have been really, really good in recent years at things like image recognition, speech recognition, and they're starting to drift into areas like text classification and things like that. The last thought I'll leave you with is the reason I think of this, and we'll go into more detail about that, I suppose, at the conference in the longer version of this talk. The reason I think this has happened is kind of a confluence of 4 different things coming together. So one is that there have been some improvements in the algorithms that people are using, but I don't think that's the main driver. People have been trying to use these sort of approaches. We saw Rosenblatt all the way back to the 1950s. There's been a steady progression of work on algorithms there. I think the interesting thing is its development of algorithms along with improvements in hardware. So this is good golden age computing to train up your deep network. You kind of start it, go away for a day and a half, and come back and see what happened. Hardware has made that feasible. It's all got nice and fast. We can do it. Particularly GPUs are brilliant for this. The data is available, which seems like an obvious thing, but it means that if we want to do something like train up a network and we need 10,000 pictures of digits, we can get that sort of thing. Right? That sort of thing is easy and accessible now. And then the last thing I suppose related to that is there are interesting applications that need this level of sophistication. So there's lots of work here, like I say, in things like image processing, speech recognition, and companies like Google and Netflix and Facebook have interesting applications where they need that level of sophistication, and that's kind of driven a cycle of research. So I think that's kind of what's interesting about why this is blown up now rather than before. So that's it basically, so thanks very much, and hopefully most of that came across. There wasn't too much noise.
Thank you very much, Brian. Yes, the second half was clearer and really fascinating stuff, so thank you for that.
No problem. I'll jump out of this and hopefully give you back that control.
Yep, we'll go back to sharing our screen. Are there any questions, Ronan, coming through? Okay, I have a few questions here for both of you, so if you could both stay tuned. We'll just go back to sharing our screen and then we will go through that.
Some of those Gmail accounts. You don't have to see that, okay.
Okay, so thanks for that, Brian and Paul. It's been very interesting take on what's the present of predictive analytics and also the future. So, question maybe for you, Paul, to start off with. So, first question I had was we have Eric Marcade from SAP speaking at the Predict conference in Dublin, and you mentioned briefly what the area he'd be talking about, but maybe you could elaborate a little bit on what Eric will talk about at Predict.
Yeah. So. Eric Marcadet is VP of Advanced Analytics and leading the entire Advanced Analytics portfolio in SAP. And while he would be talking about exploratory analytics, the idea is to show that a business user, without understanding what is the complex algorithms that are running behind the scene, can do a lot of what-if analysis, can do a lot of what would happen if I change things in my business, right? So those kinds of interactions through visualizations, wherein the visualizations are telling the story, but the insights are actually pumped in by the automated technologies that we have. And this is completely a cloud service, so it is on the service-oriented architecture, and you'll have the exploratory analytics, which we call it as Magellan, which will actually help you discover all the hidden insights in the data using the services beneath. So that is the talk around.
One other question for Paul before we move over to something for Brian is what are the, like, at a scale that SAP operates with enterprises which are global scale, what do you see as the major challenges that are preventing predictive analytics from being used in major organizations?
I think when we talk about various industries, the very fact that understanding the power of advanced analytics into their own business processes, because people from IT understands the language of IT, but when you talk about travel, when you talk about connected cars and so on, what is the value add that advanced analytics will bring forth to their business processes, something which is, so there is a lot of evangelization that I think needs to be done, and that is one primary role that I do as well. Talking to different businesses, trying to talk through advanced analytics and help them identify use cases that can make them successful. It's not about showing a fancy UI with some insights, but something that touches their bottom line revenue, and how they can increase is what the focus has to be, and that is where the major amount of the effort goes in. Putting advanced analytics is easier than actually convincing somebody or finding out use cases for them, and also having the relevant data, because not everybody has data which can help solve their problems. So identifying what needs to be captured, how it has to be captured, at what frequency, and then looking at the entire workflow. So it's a lot of talking that needs to be done before any action happens.
I think it's all about the top leadership buying into it and setting the vision, and then that asking the right questions, and then you can actually engage with the analysts. So excellent, thank you, Paul. So over to you, Brian. Paul alluded to this in his talk, that only a small fraction of the potential customers are actually going to be deep data scientists. And probably, as he mentioned, there's going to be a massive shortage of those data scientists internationally, in America and all over Europe and the rest of the world. So you teach predictive analytics to students every day. Firstly, maybe, what skills or traits do you kind of look out for that you think makes students really suitable for a career in data science or analytics?
I think actually, to pick up on what Paul was just talking about there, that's one of the key skills. So the idea to be, I suppose the skill to be able to take something like a business problem and frame that into something you can do with predictive analytics. So one of the things we kind of say in some of the courses that I teach, we say predictive analytics, while it's great, there's a very limited number of things we can do, right? So from data you can make predictions, you can predict the value, you can predict the category, something like that, but our kind of analytics toolbox only has a few tools inside of it. So one of the big challenges is to be able to take an interesting problem that people have and to say, okay, well, how can I attack that using the tools I've got in terms of analytics? So how would a prediction model go with that? And simple examples would be, there's the classic churn example. So a company says, oh, we have too much churn, what are we going to do? Well, as an analytics person, you can't stop customers from leaving and going somewhere else. But what you can do is provide some insight. And the interesting thing for people, and particularly if you go, I suppose, that elusive idea of what is a data scientist, and there's some notion that there's someone who can do everything. One of the things that people, you really look out for, and it's really great when you see it, is someone who can say, yeah, I can see that problem, and I can see how to turn that into an analytics problem and how an analytics would fit in with that. On top of that, so that's kind of an important thing. On top of that, I suppose the other thing that I like is just people who are really comfortable with data. And it doesn't even have to be terribly sophisticated. So if you get like people coming in at the start, if people are happy with spreadsheets and messing around with spreadsheets and writing a few formulas in Excel and things like that, that's a great starting point. Just being happy with measuring things and thinking about measuring things, that's a really good starting point to kind of kick off learning about analytics and getting into analytics. And then, obviously, you build on that, so you need the good stats, and if you get deep into algorithms and things like that, stats and maths is really important. But then I think that last thing, and I suppose it ties back, or the last thing I'd say that ties back maybe to that, the first thing is communication then becomes really important as well. So insight is only good if people do something with it. So being able to get out and kind of describe your results to people and explain results to people is a real skill, and something that we actually spend a lot of time teaching things like data visualization as well as that as an important thing. So there is, I think they would be the kind of those three things that we really look for. So there's that kind of problem solving skill, because ultimately that's what analytics is. That comfortableness with data and maths and stats, and then that ability to communicate at the end. It's that fully rounded kind of unicorn data scientist that we go looking for.
So it's getting, it's not just the stats and maths anymore. I think that's the key.
Exactly.
That's the key point, and I think Paul is agreeing with you here. So I think there's a certain curiosity and creativity that needs to take place to translate that stats and maths into the business problem. Maybe
Exactly.
I'll just add to what Professor said, is that when you have a traditional data scientist who is comfortable in an offline scenario, working around problems and finding insights, the challenge is when you actually want to operationalize these models in real time and put it as part of the business processes.
Yeah.
And that is where all the challenges come in, because data will not come in the way you expect it to come in. The frequency at which it comes is different. The workflows around which, because once it is in production or in an operationalized scenario, the data scientist is no longer there. It is the consumer on the other end who is there. So his interactions could be completely berserk, and he would not have ever thought of such kind of interaction. So I think the challenge is, one thing is to know your domain very well, that is the data science domain. But on top of that, the other part is that when you are actually trying to operationalize these into business processes, then also become aware of the nuances of how to get that there seamlessly without having a lot of disruption in the way you do things in data science. So.
Okay, and one final question for both of you. And Brian, you were alluding to this, that these deep learning algorithms are actually getting very, very smart, whereas they used to have 80% success rate, which would be great, in an exam for anybody, but it's not good enough when it comes to reading characters and understanding them. And you've said that with the deep learning methods, things are getting almost perfect in their ability to read data from unstructured sources, etc. So I know that the area of artificial intelligence really is starting to make a lot of progress, and recently Elon Musk and Stephen Hawking have expressed concern about the risk of artificial intelligence perhaps getting even too smart, and that the government should start to monitor and even regulate it and make sure that people don't doesn't get too far ahead of ourselves before we know it. It could become a risk to society or something. Have you read about that? And maybe over to you, Brian, first. What are your thoughts? Do you agree that should be something we're concerned about?
Yeah, I think it's really interesting there. A lot of it goes way over the top, but it makes for dramatic headlines and good pictures of people with USB ports on the back of their heads. But I think it is to break that into two parts. So one part of it is, we'll talk about this existential risk of you make this super artificial intelligence and it becomes as intelligent as us, then we don't get needed anymore. And that's all very interesting to think about, but it's definitely on a longer time horizon. But it is.
It's a possibility.
Yeah, it's a possibility. It's a long way off, probably, but it's something interesting to think about. I think the thing that's more pressing now is to think about the deep learning type stuff is very interesting from this point of view. So we're starting to be able to build systems that are very good at doing certain things. So if you think about all that deep learning stuff, things like image recognition, are becoming very good at recognizing images. There's a nice example recently. Google had a thing that you took a picture of your food and it could do a decent job of kind of mixing out the potatoes from the steak and the beans and telling you what's what. That kind of stuff is becoming very good at. And one of the real dangers is that we put a little bit too much faith into those things. So while they're good at these very narrow domains, these systems are still quite brittle and they're not perfect, and there isn't this very higher level. There aren't these very higher level processes going on that maybe we start to assume when we give them So I think it is interesting with that. So Elon Musk was involved again, and Stephen Hawking, there was a letter about military use of some of these things. And I think the interesting part with that isn't so much that, it's going to be this super smart robot soldier that's going to be made. I think the more interesting thing is that the technology now has got to a point where it's probably feasible to make an automated system that can make decisions. So you think about the drones and things like that. It's feasible to make those automated, but it's still not a good idea for lots of reasons. And I think that's the thing. It's not that these are going to. It's not that existential risk of the AI getting out of hand. It's that we're making systems. They're just tools. They're better tools than the tools we used to have, but we should be careful about what applications we decide to let those tools out. So, guessing what you have for your dinner is fine. It doesn't matter if you get that wrong every now and then. Good guys and bad guys.
It's not so good,
I think Professor has rounded up very well there. Yes, the data science is art of the possible, right? And you can imagine, and imagination has no limits, right? No bounds. So you can always imagine that there will be a world wherein everything is automated and humans are made redundant. And a very recent article on Nuggets told that data scientists are now going to be extinct because everything is going to be automation, right? And I know Roland sending me that email telling that, oh man, you are extinct now. I said, yes, I am, and I'm good that you told me now because you have in 3 years time, they said. So I have 3 years to actually upskill or get skilled in other technologies and make my life better. So I agree that yes, it is far-fetched, but you just cannot ignore those comments because it can be a reality soon as well.
One of my colleagues has said he's been putting himself out of business for 20 years. Every year they threaten that he's going to be not needed, but it still seems to have a job. So okay, I think we will wrap up. Oh, we've got a couple of questions. Oh, great. We've got a question coming in from the audience. Ronan, please go ahead.
So maybe for you, Brian, just in terms of typically how many hidden layers in a deep learning network? Is the question here from John. Are we talking millions or tens or hundreds of thousands?
So it tends to be kind of tens to hundreds maybe. The tricky thing is that each one of those layers has thousands of parameters. So in the diagram side, those little lines that we're connecting those layers, each one of those represents a parameter. And the training process of training up the network to do the job is finding the optimal value for each one of those parameters. So the reason this stuff takes so long and we CPUs and lots of processors essentially to do it is that it is a search for tens of thousands optimal values for tens of thousands of parameters. So it's a combination of not too many layers, a lot more layers than we used to have, but because those layers you multiply out the number of parameters that we need to find values from, that number of parameters explodes really, really quickly. And that's where the real challenge is, and it becomes hundreds of thousands of parameter values that we're searching for.
Okay, thank you.
The last question then is from Dan. He mentions, perhaps maybe there's something you call this, talk about the opportunities and how we can sort unstructured data. And obviously with the challenge being, circa 75% of data being in unstructured form.
I think there are immense opportunities there, and when we talk to our customers or we're talking about use cases that they have, most of the data that you understand from the customers or has significant imprint of the behaviors of the customers are unstructured as compared to what you have in structured. Structured is limited because you are interacting with an ecosystem and the interaction only captures your behavior with reference to that ecosystem. But your behavior outside that ecosystem is captured by all the unstructured means. And that is where I think unstructured mining, converting unstructured data into formats that can be mined for finding interesting insights that can supplement the decision making is picking up big time now. And we have quite a few use cases when people are looking at the audio conferences that they have with the call centers, which are converted into text automatically, and this text are mined to identify if there are new products that the customers are inquiring about, which is nowhere captured as part of the regular transactional systems, right? So identifying new business opportunities, identifying why the product has failed, identifying whether customers are unhappy or happy because of various things that are part of the features that are provided. doesn't come through regular transactions, but it comes through emails or through other forms of communications. And so definitely there is a wide scope, and we are seeing that this trend is picking up big time.
And just back to a follow-up question for you, Brian, just back to the previous question.
Yep.
So regarding the number of hidden layers and so on in deep learning networks. So the question is, typically how many nodes in each layer, and what determines the number of nodes, I guess? What drives the thousands of parameters which you touched on?
Yeah, so this is, so kind of starting point of how many inputs. So if you take the images that we were working with, or in those little examples, that's 28 by 28 pixels, so 784 inputs. And then typically the nodes of the layer put less inputs than that, but this is one of the real dark arts of using neural networks, just picking things like that. It's one of those things that there aren't great rules for, or aren't hard and fast rules for at least. But typically, it kind of depends. There's a few different approaches floating around. When we talk about deep learning, it actually covers a few different families of algorithms. One of the types of algorithms that use a lot is thing called an autoencoder. And typically they follow the picture, like the one I have in the slide, where you go through a few layers of narrowing and then a few layers of widening at the other side. So you tend to have something like, maybe in the first hidden layer, maybe 2/3 of the inputs, about 2/3 as many nodes as there were inputs, something like that, and then slowly kind of narrow down and then go back out again. And then the other approaches will work different, but it's one of the interesting things about these deep learning approaches. So while the kind of headline promise is we just throw in the data, and we throw in the very rawest data, and the network learns everything, the reality is a little different from that. There's a lot of hand-holding that needs to go on. There's a lot of choices that we make about architectures and networks, things like number of hidden layers, number of units, and all that kind of stuff that has a big impact on what actually happens. And that is a bit of an art rather than a science in some cases.
Okay, thank you. So getting into some of the details, maybe that's giving you some ideas what people want to hear about at the conference, Brian. So excellent. Thank you for those questions, everybody. I think that leads us to wrap up. So I'd like to just thank again SAP App House, and thank you, Paul, for hosting us here today. Thank you, Ronan, for organising. It's been great sitting here. We're looking out the window at a sunny day in Ireland with the traffic flying by on the N7. So it's actually, the weather is great here. So this is the final webinar in the lead up to Predict. So the next thing is the actual conference itself, which is of course on the 15th and 16th of September for the main 2 days of the events. The 17th are the workshops. Following that, we will have a revision webinar after the conference, so you'll be welcome to join us for that, and that'll be actually hosted by Aon at the Centre for Innovation and Advanced Analytics here in Dublin, and Aon are going to be a big part of the conference, helping us out with our data genies in particular. So I'm looking forward to meeting them and to having them introduce all of the different stakeholders in the event. So I think that's it for today. So thank you, everybody. Thank you, Paul. Thank you, SAP, for hosting, and I will see you in September. Thank you. Bye.
Thank you very much.